Hello everyone and welcome to day 3, looking at continuing to look at the fundamental theorem of calculus. We did part 1, which many textbooks and mathematicians call part 2. It doesn't really matter which one it is. But what we talked about last time was exactly what's written here. The integral from a to b of f of x dx is the integral evaluated at b minus the integral evaluated at a. And you guys already did work on that. What you guys worked on the discovery portion of in last class was the fact of right here, that the derivative of an integral from a constant a to any x value of a function f of t equals the function with respect to x. And why is it with respect to x? Because if the integral has a variable x right here that can move anywhere, I've put on Schoology a Khan Academy video that does a very good job at explaining a fundamental theorem of calculus. If the discovery lesson did not work for you, I would highly suggest at least watching the first 4 to 5 minutes of it. It does a nice job. But since the bounds are in terms of x, we need the function in terms of x here. What I'm going to do right now is put up in the screen why this derivative of an integral works and why it needs to be in terms of x. And so what this is if we say that the capital F of x equals the integral of a to u of x being any point on the curve with respect to x, that's what this is right here, of the function f of t dt. If we take the derivative of it, we know that the derivative is this derivative of u of x subtracted from the derivative at a. And when you do this, you're going to get f of u of x. You plug in u of x, but you have to multiply by the derivative of u of x, which is u prime of x, subtracted from f of a, plugged in a, times the derivative of a. Well, if a is a constant, what we know is that this can just go to 0. And so therefore, using the fundamental theorem of calculus, we can state that the derivative of this function, or this integral, is f of u of x multiplied by the derivative of u of x. In this case, if we look at it, we have f of x multiplied by 1. And so that's why we don't have this u prime of x here, because it's really just multiplied by 1. The derivative of x is 1. And so that's where we get f of x. So hopefully that helps a little bit. Let me show you this. Let me do this the long way and I'll pause it in. I'll do it the long way. You don't need to write this down. So what did I do? Well, I evaluated the integral just how we learned how to do it. So t to the 4th over 4 from 1 to x. I plugged in x, I plugged in 1, you get x to the 4th over 4 minus 1 to the 4th. I'm taking the derivative of all of this. I haven't done anything with the derivative, so I'm going to take the derivative of x to the 4th over 4. I'm going to get 4x cubed over 4 minus the derivative of a constant, which is 0. 4x cubed over 4 is just x cubed. Notice that if I hadn't had to do it the long way out, if I would have just realized that the derivative of an integral, I'm going to take this and plug it in and multiply it by the derivative, is just x cubed times 1, which equals x cubed. This is a shortcut way for doing it the long way out, but it still does work. If I wanted to, I could take the integral and then take the derivative of it and still get the correct answer. So take some time if you need to, pause it, and look at that. The last part is this true? The integral from -1 to 1 of 1 over x squared dx. Well, I can rewrite this as x to the -2. If I take the integral of that, I'm going to add 1, so x to the -1 over -1, and I'm going to get -1 over x. And when I plug in 1, I'm going to get negative is in parentheses, so I'm going to get 1 plus, or 1 minus a -1, which is a plus. And I will get -2. Is that true? Well, let's look at what 1 over x squared looks like. Very poor version of that. But 1 over x squared looks like this. The key thing of doing any integration is the fact that it must be continuous. So do not let this fool you. This is not continuous over the interval of -1 to 1. And so therefore, this is not true. It's not continuous at x equals 0. Now, let me state this. If I had asked you -3 to -1 of 1 over x squared dx, that you can do. That you can actually solve because it is continuous over this interval. But if we're looking at this example, -1 to 1, it is not continuous over the interval. So therefore, you cannot say it is -2. So let's look at a few examples here. I hope that this is going to come quick now. You realize that we have the derivative of the integral from 0 to x. Notice that it is a constant in the denominator, or in the lower bound, so it does work. So all we're going to do is plug in x. We're going to get 1 over 1 plus square root of x. You can multiply the x times 1, but you don't need to really write that because we just know that it is 1 over 1 plus square root of x. That's it. Now in this case, you'll notice that we have x squared. So that's where the problem, just the extra work comes in. We get ln of x squared multiplied by the derivative of this, which is 2x. So we can get 2x ln of x squared. And we're done. So I'm going to have you guys try this. Find f of 0, that should be very simple. Find f prime of 0, simple again. Find f double prime, you are going to have to use quotient rule. So take a minute and try that. And so the integral from 0 to 0 is 0 because there is no area. F prime of x, notice that you'll see that I found all the derivatives, the second derivatives, before subbing in 0. I found the general one with x, and then I plugged in 0. So I found the derivative, sine x divided by 3 minus x, and then plugged in 0. This is sine of 0, which is 0. The same thing for the second derivative. I know it's the derivative of the first derivative, and so therefore I'm going to take the derivative of sine x over 3 minus x, which is quotient rule, and I did the work out there. Plugged in 0. After I found the second derivative, I plugged in 0. So pause it if you need to. Take a look. We'll go on to the next page. I'll have you guys try these next two problems on page 3. When you're done, unpause it, and I'll have the answers. So the mistake you guys might have made on this one is that you forgot to plug in 2x, and all you did was plug in x. And you need to take the derivative of 2. I plugged in 2. 2 times 2 squared, 16, minus 4 is 12. And on the last one, shouldn't be a huge problem. You get cosine of x cubed multiplied by the derivative of x cubed, which is 3x squared. So there you go. So moving on to the mean value theorem, we talked about mean value of derivatives, mean value theorem for derivative. Now we're going to be talking about the mean value theorem for integration. What this states is that the area under the curve of a to b, which would be from here, and then I could draw that all the way down to here to there, right? That's the area under the curve. What that's saying is that that area under the curve can be represented by a rectangle that is drawn. F of c is a y value. Right here would be that y value. That's the height multiplied by the width, which is the a to b, or length. I don't care which one you call it, but you got height multiplied by width. So the area under the curve that was in blue that I had will equal at least 1 point, but usually at only 1 point, at that y value, at where x equals c, will equal the exact value of that rectangle that is drawn, height times width. And so the goal is to find that height, that specific height, at that x value of c, and where does that occur? So if we look at this next example, it says find a value for c in the interval 1 to 4, which satisfies the mean value theorem of f of x equals x squared. Now c, it should really say find a value for x that represents that. C is the value for x. So what we can write down is the integral of 1 to 4 of x squared equals f of c times b minus a. Well, we know what this is. We can easily do that. It's x cubed over 3 of 1 to 4 equals f of c times b minus a. Well, that's just how far the width of that, which is 3, changing the bounds. And so we can say that this is 4 cubed, which is 64 over 3 minus 1 over 3 equals 3 times f of c. And this is going to be 63 over 3, which we know is 21. So we can say this is 21 equals 3. F of c, well, it's just going to give us c squared. Well, we can divide that, so we can get 7 equals c squared, and so we can say that c equals plus or minus square root of 7. Now, we know that we're within the interval of 1 to 4, and so therefore we know that c has to equal the square root of 7. So to recap, all I did here was basically copy down the definition of the mean value theorem. I found the integral, found the width of the bounds. I solved knowing that f of c, well, if f of x is x squared, we know that f of c is c squared, and then solve for c. That's it for the lesson. Again, I want to say that the fundamental theorem of calculus does not fully click. The Khan Academy video is excellent. Other than that, I'll see you in class. Have a good day.